Hello to everyone, I'm Lucas Pavlov. I'm a PhD student from the University of Buenos Aires, and today I will present the work Oscillating Bubbles Rising in a Doubly Confined Cell that I did as part of my PhD and in collaboration with the Institute of Fluid Mechanics in Toulouse, in France. So the aim of the study is to gain an understanding on the behavior of freely rising bubbles, that is, bubbles that rise solely because of the effect of gravity. And in order to do that, we chose to perform an experimental study in a thin-cap cell that has several applications, such as, for example, in photobioreactors. And in addition, it allows an easier experimental analysis as compared to the three-dimensional case. There are several related works, either numerical or theoretical or many experimental works in this subject of bubbles rising in a thin-cap cell. But what we did differently is that we introduced an additional lateral confinement that can be used to modify the coupling between the bubble path, its shape, and the flow induced in the surrounding liquid. So the main questions that we asked ourselves are what will happen to the bubble rise velocity, to its shape, and to the oscillations of the bubbles in the presence of the lateral confinement. Here is a scheme of the experimental setup, which consists on a cell of thickness 2.8 millimeters that is filled with distilled water, and air bubbles are injected in the bottom. The width of the cell can be modified from 2.4 to 21 centimeters using internal walls, and we compare the results with a case of 40 centimeters of width from the literature from a cell of a similar gap thickness. The governing parameters of the problem are parameters that characterize the liquids or the geometry of the cell and the size of the bubble. And the parameters that we varied throughout our experiments are the lateral confinement of the cell, that is the width of the cell, and the equivalent diameter d. So 6 independent non-dimensional parameters can be formed from this set of dimensional parameters that are the density and viscosity ratio, that are constant and very small. This parameter h over d, that actually it's always less than 1, which means that bubbles are flattened between the two plates of the cell. This parameter xi, that is a non-dimensional measure of the space that is here available for the fluid to move between the bubble and the lateral walls, and the Archimedes and the bond number. And it is important to highlight that we are in an inertial regime. The Reynolds number and this Reynolds number in the cell are both greater than 1, which means that the regime is inertial even though we are in a thin-cap cell. So in the problem of bubbles rising, either in 3 dimensions or in a cell, several rise regimes can be observed. In this talk, I will focus on the regimes that have oscillations, and mostly on those regimes that have path and shape oscillations, or in the end I will say something about this regime that appears when there is lateral confinement that has only shape oscillations. And so those are all the measurements that we perform, and the color here, each point represents a bubble, and here we have the different regimes, and the shape of each symbol represents the regime, and the color represents the width of the cell. Okay, so here is an example of an oscillating bubble. I wanted to show actually that the magnitudes that characterize the movement oscillate in time and around a mean value that we will use to characterize it. Either the velocity, here it's the vertical velocity, which has a mean value v sub b, or the horizontal velocity that has a mean value of 0. And here I show this parameter chi that characterizes the shape of the bubble. So it's a measure of the elongation of the bubble. can be obtained from the ellipse that best fits the bubble contour. So here in this curve, we show the mean velocity and shape of the bubbles, and actually for all the regimes, but I will focus on these regimes, the regimes with path or shape oscillations. And well, what we can see even from this plot is that for a given bubble size, the stronger the confinement, the lower the rise velocity, and the more rounded the shape, that is chi closer to 1. And we can say that the effect of the confinement, which is the departure from the non-confined case, can be seen earlier for the bubbles, for bubbles that are smaller in the velocity as compared to chi, to the shape. So here we show these critical bubble sizes. So the black ones are for the velocity and the red ones for the shape. Actually, the field symbols represent the diameter and the value of chi or the velocity when the bubbles depart from the non-confined case, and we can see that for every confinement the value is smaller for the velocity. So it can be seen earlier, the departure in the velocity as compared to the shape. And okay, well, here, well, the next thing that we wanted to do was to understand what happens to the velocity of path oscillating bubbles. And well, here is a non-dimensional representation of the plot that we've seen and that we have seen earlier. That is the Reynolds number as a function of the Archimedes number, and the Reynolds number defined based on the bubble rise velocity. And well, we can see that the Reynolds number is lower for the stronger confinement, as we have seen before. So we wanted to understand why this happens, and we performed a simple argument using mass conservation. So when the bubble rises with a mean velocity v sub b, the flow around it must have a downward net velocity u sub f in order to satisfy mass conservation in the cell. This u sub f can be estimated like this if we approximate that the mean width of the bubble is equal to its equivalent diameter, and we can calculate the mean relative velocity between the bubble and the fluid as the sum of v sub b and u sub f. That can be written in this way in terms of v sub b and of the non-dimensional parameter xi that we have defined before. So if we use the Reynolds number based on the relative velocity between the bubble and the fluid, we can see that this Reynolds number is actually independent of the width of the cell. It only depends on the size of the bubbles. So this means that the relative velocity between the bubble and the fluid is constant, independent of the bubble of the cell width. It depends only on the size of the bubble. This is a strong result that can be used to generalize the expression for the velocity that was given in the literature in order to account not only for the thickness of the gap, but only for the width of the cell. We also studied the amplitudes of oscillation, and here we see the amplitude of oscillation of the vertical component of the velocity normalized by the relative velocity between the bubble and the fluid. And we see that actually is this relative velocity that is the relevant parameter for the normalization. And actually, since the relative velocity is independent of the lateral confinement, and here this amplitude of oscillation of this component of the velocity is also when normalized by URL, it's independent also on the lateral confinement, which means that actually the amplitude is independent on the lateral confinement, even though the mean vertical velocity depends on the lateral confinement. And here we show the amplitude of path oscillation, and we see that the lateral confinement does not have a strong influence, except
for those bubbles for which a bouncing effect can be observed. We said a bouncing effect because it's the presence of the presence of the lateral walls that doesn't allow the bubble to have a larger amplitude actually, and it's like it bounces because of the lateral walls. And this bouncing effect can be seen not only as a decrease in the amplitude, but also as an increase of the frequency of path oscillation. But apart from that, from those very confined bubbles, the frequency of path oscillation is unaffected by the lateral confinement. So we can say that the relevant velocity here is also the relative velocity between the bubble and the fluid, and that the path wavelength is smaller for stronger lateral confinement because the mean velocity is smaller for stronger lateral confinement. This has a strong effect on the wake behind the bubble because since in every period two vortices, one at each side of the bubble, are shed, the number of vortices shed per unit time is the same no matter the confinement, but in a more confined bubbles there will be more vortices per unit length since its wavelength is smaller. Finally, I would like to say something about the bubbles that have only shape oscillations, and this regime appears only in the presence of lateral confinement. If there is no lateral confinement, the bubbles of this size they don't have an unstable rise regime. They have path oscillations that are unstable and with no clear periodicity. And in this sense, the lateral walls have a stabilizing effect on the bubble. And here we don't have a frequency of path oscillation because there is no path oscillation. So we use the frequency of the parameter chi in order to characterize the frequency of the bubble. And we compare it to the frequency of chi for the path oscillating bubbles, that is the double of the frequency of path oscillation, actually. And we can see here those are the bubbles that have only shape oscillations, and we can see that they actually have the same frequency of shape oscillation that the bubbles that have path and shape oscillations that are a bit smaller than them for the two confinements that in which we observed this regime. So with this, I would like to finish my presentation. I thank you all for listening, and I will be pleased to answer your questions. And also, if you want more information on this work, I refer you to our paper that was recently published in Physical Review Fluids. Thank you very much.